Hello, everyone. Welcome. So today we're very happy to have Maribel Bueno, who will tell us about eigenvalues you did not know existed, and how you like people to ask questions.
Oh, so I actually, I wanted to tell you a bit about what has happened with this talk and how I would like to interact with you guys. So, first of all, Simon asked me, is that what you're asking, Simon, that I tell them how I want them to interact with me?
Yeah, do you want them, so when they have questions, do you want them to unmute
Yeah,
and talk
okay.
or type in the chat, or what do you prefer?
Okay, that's exactly what I want to explain. So, first of all, when Simon told me to prepare this talk, he told me, talk about something that is related with your own research. And so I thought, oh, I know exactly what I want to talk about. But then when I started preparing the talk, I started reading some papers and found some papers on things that I did not know actually. And they actually sounded more exciting than the ones I was planning originally. So what I want to tell you guys is that what I'm going to tell you about is something that I am learning on the right now. And so I may not have all the answers, but actually I think it makes it more fun. And so I want you to participate anytime. So you can just unmute yourself and ask a question, participate. And moreover, I don't know much of your background, so I don't want to assume that that you know something. So you can also interrupt me anytime if any of the concepts I talk about are unfamiliar to you. And also, moreover, I have written the slides in a way that requests your participation so that we can have a conversation as we go. So I hope that you get involved. Is that okay, Simon?
Yeah, but do you want them to type in the chat or just talk?
No,
Which,
no, don't. If they type in the chat, I won't see what they are writing. So
okay,
if you just what we can do is if you raise your hand, then Simon can tell you to he can call your name so in case several hands are up. Is that okay with you, Simon? You can see
yep,
that?
yeah, that's
Yeah?
fine.
Okay, fantastic. So let's just get started. I'm going to get started. Let me see. Oh, I don't know why it's not working. Okay, let me see. Oh, sorry. I have seen this before happening in other talks. Okay, so if I do, mhm. If I do a slideshow, it's going to start moving by itself, right?
I don't know.
Okay, let's just try that. Okay, so let's just go to the first okay, slide. Okay, so we have here two pairs of graphs. So a graph, in case you're not familiar with, is just a set of dots connected with segments or lines or called edges. And so my question to you is quite vague, actually. If you look at Q1 and Q2, and then you look at X1 and Y1, my question is, do you think that any of these pairs of graphs are similar? If you think they are, why? If you think they are not, why? And if you can give a score from 0 to 1 on the level of similarity between them. Okay, so let's just start with that. Who would like to answer that question?
I would say X1 and Y1 are more similar because it's like only a one line difference.
You mean X1 and Y1? Because there
Yeah.
is only one what?
I think because there's only like a one line difference, you're just moving one line.
Oh, you mean the edge? That
Yeah.
edge is moved to
Yeah.
the right? Okay, okay. More,
Um,
more, more
X
opinion.
and Y, sorry, X1, Y1 are like mirrors, opposites of each other. Like there's some reflection property perhaps.
Okay. Okay, it's not exactly a reflection, but I see what you mean, right? It's not exactly a reflection because of this edge here, right? The edge on the right, on the left. But yeah, there are a lot of symmetries there. Absolutely. Anyone else would like to give an opinion?
Like for Q1 and Q2, like if you like take those two nodes in the middle
Yeah.
and you like basically duplicate them, and then you like basically break the graph in half, and then you kind of glue the two edges on the other side.
Uh-huh.
Like if you do that to Q1, then it becomes Q2.
Okay, so what you're saying is that we can do some transformations to the graph that would make it more similar to Q1. Is that right?
I think you can like do a transformation, like you can like basically duplicate edges and then like glue it back together to make it exact, like to make Q1 exactly the same as Q2.
Okay, so as you can see, you are coming up with a lot of ideas on how to measure similarity, right? Okay, but let's just go to my
Oh,
question.
there are several other people with hands up. So Benjamin,
Okay.
Similarity I see between Q1 and Q2 is at least if every node was swapped out with an edge and every edge became a node, I think it might become the same.
Okay. Oh, that's a very interesting observation. Okay.
okay,
Okay. Ayush.
Um, for Q1 to Q2, if you move the bottom two edges of Q2 to the top, you get Q1. So you need to move two edges, whereas in X1 and Y1, you only need to move one edge to get the other graph.
Okay. 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 I think I said Ayush now that is raising their hand. Oh, Araf. Araf.
If you invert that triangle in Q2, both the triangles, then it becomes Q1.
Okay. Okay, so I'm not going to take any more answers right now because otherwise we would not be able to move on. But the whole idea is that I wanted you to have the the thought about what does it mean to be similar. And as you can see, similar for each of you means very different things, right? So in general, okay, so we will get to what similar means in this talk in a bit, but thank you so much for your participation so far. Okay, so oh my gosh, why it's not working again? Ah, I don't know why it's not working, Simon.
I don't know.
Oh, okay. Oh, okay. No. Okay, so as I was saying before, I don't know if I have mentioned that in data science, for example, graphs are a very good representation of a network, right? A network represents, for example, connection between cities with roads, or it could mean connections between in a social media connection between peoples and friendships, or links between websites, etc. And so in that area of mathematics, and in many others actually, it is important to determine when those networks are similar. And so as you can see, when the graphs are small, you can give an opinion based on what you see, right? You were saying, oh, I look at these cycles, or I look at these edges, or I look at these nodes, and you can give an opinion based on your context on why they are similar or not. But when the graphs become very large, then it's impossible to do that by inspection, right? So what we are going to be looking at the question is we can find some mathematical fingerprint that we can use to determine that similarity. Okay? So as I was saying, is that this is an interesting problem in different fields. One of them is social network, as I was saying. It is also very interesting in chemistry when you are checking comparisons between molecular structures. And obviously in computer science in general is an interesting question. But let's go to the math itself. So we are going to be focusing on a very specific type of graphs. They are connected, undirected, and simple. Okay, anyone can tell me what simple means? Okay, simple means that we don't have loops, and loops are edges that connect an edge with itself. And simple also mean that we cannot have more than one edge between the two nodes, okay? And what is undirected? Do you see what undirected is?
like the edges don't have directions.
Exactly. The edges don't have direction. So if one is connected with zero, zero is connected with one. Imagine if we were talking about, for example, roads, you could have a directed graph when you have a one-way road, right? And connected means that you can go from any node to any other following the edges. Okay? Okay, perfect. Okay, so this is the first idea that researchers came up in an area of mathematics called a spectral graph theory. And by the way, at the bottom of the slides, I'm going to be adding the references in case later on you want to check them out. So the first idea that they came up with was, okay, every graph has an adjacency matrix. Let's compare the eigenvalues, okay? So, okay, so let's see if you tell me if you're familiar with the idea of eigenvalue. Anyone can tell me if you have a real matrix, what is an eigenvalue and what is a right eigenvector?
Can I speak?
Okay, Jason, go ahead.
I guess generally it's just like a scalar where if you apply it to a vector, then it'll spit out a scalar multiple of that vector. And so the eigenvector is that vector associated. I had a question about this because isn't it, since it's not direct, doesn't that technically mean every matrix or adjacency matrix is symmetric? Or
Yes,
maybe
yes,
symmetric as well. But yeah, okay, cool.
that is exactly right. I mean, we are going to talk about the adjacency matrix in a second, but you are totally right. Okay, so what Jason was saying is that an eigenvector is a vector x, and actually we need to request that x is non-zero, okay? Such that ax equals lambda x, and lambda is a scalar, and that's what we call the eigenvalue. Everyone is good with that? Okay, so based on this idea, let's just go to the, oh, okay. Okay, so just briefly, geometrically, what that means is that if an eigenvector is a vector that under the action of A remains in the same direction. So the lambda, what it does is it stretches the vector, or depending on the sign, it keeps the same direction or changes the direction. Okay. Okay, so let's go back to the question that Jason was mentioning. So if you have a connected and directed graph, which is also simple, how do we construct the adjacency matrix? So we pick, I mean, this column here and this row here are just the number of the nodes. And what we are going to do is we're going to compare one with one. So is there an edge connecting one and one? No, because we have chosen a simple graph. So all the main diagonal entries are going to be 0. And then 1, 2 is going to be either 1 or 0. 1 if they are connected and 0 if not. So 1 is connected with 2, so we have a 1, right? Okay, so why is it connect? What property of the graph makes the adjacency matrix symmetric?
It's undirected, of course, right?
Exactly, it's undirected. Good, good, Stephen. Okay, perfect. So the idea is if we have two graphs and they have the same spectrum, and by a spectrum I mean the adjacency matrix, are they similar? That's the question. Okay, before we move on, what do you think? Are they going to be similar? Any guesses?
Won't they like literally be the same graph?
Can
Like
you repeat
isomorphic?
that, Stephen?
Won't they be like isomorphic? Like literally the same graph?
Okay, that's what you would hope for, right? I mean, two graphs are isomorphic. What does it mean in terms of the matrix? In terms of the matrix means that I can permute the rows and the columns, right?
Yeah.
And with a matrix and with a permutation matrix and its inverse, right? That's basically what we are doing is relabeling the nodes. Very good. Okay, so that's what we would hope for, right? That they are isomorphic. Okay, let's see what happens. Okay, so two graphs with the same eigenvalues are called cospectral. And cospectral graphs have exactly the same number of nodes and edges. So what do you think now with that information? If two graphs have the same number of nodes and edges, are they similar? Okay, it's
Wait, did we define what similar means?
That's a very good question. That's a very good question. I mean, okay, so the idea is, do they look pretty much the same? I mean, remember that question that Stephen asked, right? He said, "Oh, I was hoping that they are isomorphic." So the most ideal graphs are two graphs that are isomorphic, right? You just relabel the nodes. So basically, they look the same. So in this case, similar means they look pretty much the same with small changes. That's the idea here. Okay, so look at these two.
Yeah.
Q1 and Q2, the ones that we saw in the first slide, they are cospectral. They have the same eigenvalues. Are they similar? I mean, obviously, as Tanvir was saying, what do we mean by similar? So if we mean by similar that they look pretty much the same, obviously Q1 and Q2 do not look the same, right? I mean, actually, many of you have said, oh, you have to do transformations in order to make one to look like the other. So the idea is, without making any transformation, do they look pretty much the same? And I think that you would agree that these two are not very similar, right? Is that, do you agree with that?
Yeah.
Yeah.
Okay. Okay, so this was the first attempt, computing eigenvalues.
So,
Yeah.
do you quantify similarity by the number of transformations you have minimum number of transformations you have to make?
Actually, still that's a very good question. What I want to to walk you through is what researchers have tried to define that kind of similarity, right, in different ways. So in this way, with the eigenvalues, the only thing that we can guarantee is that they have the same number of nodes and the same number of edges. And you would agree that that information, that if two graphs have that information in common, you are not saying much about how similar they are. But in general, in the literature, I haven't seen any. I mean, the idea of similarity that I'm talking about is not the one that you're mentioning about making transformations. It's just how alike they look like without touching the graphs. That's the idea. Okay, so they are more similar the closer they are to being isomorphic. Does it make sense?
How do you prove that cospectral graphs have the same number of nodes and edges? And also, is the converse true?
Okay, so the idea is that's a very good question. Since I don't have time for that to answer, is that okay if I send Simon later a paper where you can see that?
Sure.
Perfect. Okay, so let's move on. Okay, the second idea that the researchers found was comparing the eigenvalues of several matrices related with a graph. One single matrix doesn't give me enough information. So how about if I look at several matrices? And so remember that cospectral graphs are the ones that have the same eigenvalues. And so if they have the same eigenvalues, the adjacency matrices have the same characteristic polynomial, right? So what the second attempt was the following. AG, in this case, represents the adjacency matrix of the graph. And if you want to talk about the characteristic polynomial, you would not have the last term, right? You would have the determinant of lambda I minus AG. So what the researchers did is, okay, we are going to add a second parameter that I'm going to call mu, and dj is the matrix, the degree matrix. So it's a diagonal matrix whose main diagonal entries are the number of edges that are connected to each node. And so what happens is that actually by adding this third term, what we are doing is evaluating the eigenvalues of many matrices related with a graph, okay? So what happens? If mu is 0, what we have is the characteristic polynomial. So we would have the regular eigenvalues of the adjacency matrix. But if we use, for example, lambda equal -1, we have a well-known matrix related with a graph that is the signless Laplacian. And if we use minus lambda and 1 and multiply by a sign, we get the characteristic polynomial of the Laplacian matrix. So as you can see, changing mu, what we are doing is capturing a lot of other matrices that are connected to the graph. Right? Any questions about that? Okay, so look at what they discovered. Because spectral graphs relative to this new characteristic polynomial, they have the same information as before, obviously. They have the same number of nodes, the same number of edges, and now we also can guarantee that they have the same degree sequence. So what does that mean? That the number of edges adjacent to each vertex is the same. So we are providing more information. Sounds good?
If two graphs are co-spectral relative to that function, does that mean that they have like the same eigenvalues for every value of mu?
Okay, so what we are capturing, that's a very good question. What we are here doing is calculating the eigenvalues of the matrix AG minus mu DG for whatever mu, right? So all those shifts of the adjacency matrix have the same eigenvalues.
All right, thank you.
Yeah. Or equivalently, all these polynomials have the same roots. Very good. Okay, so what do you think? Are Q1 and Q2 cospectral in this sense? Okay, actually, okay, remember they have, okay, let's just count nodes. They have three, they have, yeah,
They
but
are not right.
yeah,
They're not right. Because in Q2 there are two vertices with degree 3, and in Q1 I think there isn't. If I may have counted it wrong, but I guess that would be the idea.
yeah, exactly. Or for example, even easier, this one over here has, but it's exactly your idea, Kana. This one has degree 5, right? And here clearly you don't have any node of degree 5. But you here you have this one with degree 3, and here we have 2, 2, 5, 1, 2, 2. Exactly. So with these RF, yes.
Can you define the simplicity of a graph as the trace of the matrices forms?
Sorry, I didn't understand your question. Sorry.
Can you have like a notion, like, I mean, is simplicity of a graph as a trace of the matrices it forms, and can you do anything about it?
You know, Araf, I have to apologize. English is not my first language, and right now I'm not understanding your question. Simon, can you tell me what Araf is asking?
Wait, so can you say it again?
So can you is there a common notion for the simplicity of a graph as the trace of the matrix it forms?
Yeah, can you see the simplicity of a graph in terms of the trace of a matrix?
Oh, the trace of the adjacency matrix is 0, right?
Yeah.
Yeah.
Yeah, so that is
Yeah.
for a simple graph. So
Oh, yeah,
for more
exactly.
simple
Yes,
graphs.
simple means that the trace is all zeros. I mean, actually more than that, right? Because I mean, all but the trace is 0 means it's more than the trace. Is that all the main diagonal entries have to be 0 because we don't have loops, right?
Yeah, well, so it should mean that it's a symmetric 0, 1 matrix with trace 0. That should characterize adjacency matrices.
Okay. Is that your did I answer your question, Araf?
I mean, like, yeah, sort of.
Okay, so simple means it doesn't have loops. So in the adjacency matrix, all the main diagonal entries are 0, right? And then because it's simple, the entries have outside of the main diagonal, they all have to be 1. You cannot have more than one edge connecting two nodes. Okay? So it has to be a
Yeah, so I mean, like, Can you quantify whether a graph is like say more complicated than an other by the trace of its adjacency matrix?
I mean, the trace, okay, so obviously if the trace could also be zero, even though you don't have main diagonal entries equal to zero, right? So the trace,
But how can you have a negative component in the adjacency matrix?
oh, actually you have sign graphs as well. Yeah. So, I mean, the thing is that the graphs that we are talking about are unweighted or assuming that the weights are one. But in practice, actually, I am doing a research project with some students in which the graphs are signed. So they have weights and they may be negative. Yeah, there's a lot of possibilities for graphs depending on the context. Okay. So let's move on. So as you guys said, these are not cospectral. And which is a good thing, right? Because it means that this new strategy distinguishes the graphs better. And so can we say now that they are similar by adding this extra information? What do you think? Do you think that this extra information will distinguish isomorphic graphs, for example? Okay, so actually look at these two graphs, M and N. The two of them have the same nodes, the number of nodes, the same number of edges, and they have the same degree sequence. However, they are not completely similar, right? For example, you here have this square cycle. Here you have this triangle, this cycle of length 3. So even though they are more similar than these two, they still you cannot say that they look the same, right? So one of the reasons is that we are missing information about the cycles that we have in a graph, and they are important as well. So this is another idea that the researchers thought about, which is comparing cycles of the two graphs. So, and for that, what they did is instead of using the determinant, they use something that is called the permanental polynomial. So if you think about, imagine a 3 by 3 matrix, when you are computing the determinant, right, you have some, you multiply some diagonals there, and then you subtract the product of the others, right? So you have some positive terms and some negative terms. So in the permanent, basically what you do is the negative terms, you just make them positive. So everything is positive. You don't subtract. So if you have a 2 by 2 matrix, it would be AB plus C times D, basically. So using the permanental, now you can talk about a per spectrum, and you can talk about two graphs being per cospectral if they have the same per spectrum. And look at all the information that you preserve using the permanental polynomial. The number of nodes, the number of edges, the number of triangles, which are cycles of length 3, the length of the shortest odd cycle is also preserved, the number of the shortest odd cycles, and whether the graph is bipartite or not. Bipartite means that you can split the nodes into two pieces such that the nodes in one of the pieces do not connect with each other, and the same thing with the other group, right? Okay, now we have a lot of information, right, with these permanental polynomial roots. So what is your guess? Is this going to be enough? What do you think?
It
I
feels
guess
Stephen,
oh,
yeah.
I guess okay, go ahead.
okay, it feels like the thing gets it feels a bit random, I guess. Like I'm guessing it's probably not enough. Like
Not enough. Okay. Okay. By now I cannot trick you anymore, right? I have
exactly.
already. So that is psychological answer. Good for
I
you,
guess
Stephen.
I guess what we're really trying to do is trying to find a characterization of when two graphs are isomorphic, I guess.
Uh-huh.
uh,
Exactly. I
which
mean,
can be which like a nice characterization in terms of like some polynomial or involving the adjacency matrix.
explain it better than I would have ever done. Cannot. That is exactly the goal, to find some polynomial that whose roots allow you to characterize isomorphic graphs in a unique way. Excellent, excellent observation. So
Like,
as
do
a
we need,
yeah.
for the permanential polynomial, do we need like the extra parameter mu as well or not?
Oh, wait, we will get there. Yeah. You guys are so smart. Okay, so these are two examples. This is an example of a pair of percospectral graphs, as Stephen was guessing, right? They have the same number of nodes, the same number of edges. There is only one triangle in each of them. They are not bipartite. So as you guess, these two graphs are not similar, right? In the sense of being isomorphic. And so it's not enough, as you guys were guessing. And as Tambir was saying, they also thought, okay, let's just do the generalized permanental polynomial, right? Very good. And in this case, look at this. This polynomial distinguishes all graphs of order up to 9, which means what Kanad was explaining. If two graphs have the same generalized permanental polynomial, they are necessarily isomorphic for graphs up to order 9. By the way, that paper in which they talk about this, which is quite recent, is from 2019 actually. They don't write a proof. What they do is they use a computer to try all possible graphs and check it out with a computer.
Wait,
Okay.
but aren't there an infinite number of graphs?
Say that again.
Wait, how does that prove anything though? It's like there's an infinite number of graphs, right?
No, what they are doing is creating all graphs with 9 nodes, all graphs
Oh, okay.
no, 8 nodes, all graphs with 7
Oh,
nodes in a computer, right?
yeah.
And
Yeah.
they compute the generalized permanental polynomial and the roots. It's a very time-consuming task, right? But that's what they did. They computed them all, and then they checked. And actually, in this particular case, things work out for graphs up to order 9. Yes, Ryan.
Wait, did they find a counterexample in order 10 or could they just not check it?
Guys, okay. So what happens with order 10 graphs? Very good question, Ryan. So what they found is that it's quite efficient, but it doesn't distinguish all of them. There is a few pairs which have a common GPP, which are not isomorphic. And this is an example of pairs of graphs. I mean, this one is the X1, Y1 is the one that I showed you at the beginning, right? And then you have X3, Y3. They are quite similar, right, in this case. So even though they are not the same, they are quite similar. By the way, this is all that's known about the generalized permanental polynomial. So this is an open question. I mean, if you can do the same good with higher order degrees, right? If in case you're interested in doing some research about this. So, okay, so what is the problem? I mean, all these strategies that we have explained so far, they use all polynomials, as Kanad observed. And what is the problem with this approach? It only allows comparison between graphs with the same number of nodes, right? The generalized permanental polynomial is actually one of the problems is that computing it is very difficult. It's high, computationally speaking, is a very difficult task. And as you guys have already noticed, they don't provide a clear measure of similarity, right? They just said they have the same nodes or they don't. They have this information in common or they not, or they don't. So, so the question is there a reasonable way to measure the degree of similarity between two connected graphs? So what we're going to do now, and this is the most recent research studies on in the literature, consider the class of all connected graphs independently of the number of nodes, okay? And the goal is to create a function that assigns to each pair of graphs a real number And we are going to call this function a similarity index if it has the following properties. First of all, it's symmetric. Obviously, if G is similar to H is similar to G. We are going to assign values between 0 and 1. That's not important, but. And then if two graphs are isomorphic, they are going to be assigned the largest value. So one means very close to, one means isomorphic. And actually 0 is going to mean that they are very different, basically. So there is like a continuum from 0 to 1 in terms of similarity. And the fourth property, which is the important one, as Kanat said, is that if two graphs are assigned the value 1, then they should be isomorphic. This is what's called a graph invariant, right? It allows us to distinguish if they are isomorphic or not. So this is what we are going to call a similarity index, okay? Okay, so the fourth idea in the literature is comparing the Pareto eigenvalues of the graphs. And I think that this is going to be a new concept. This is a result from 2021, so it's quite recent. So the idea is that you construct the adjacency matrix of the graph, and we are going to compute a set of numbers, which is always non-empty and finite, which we call the Pareto spectrum. And we are going to explain in a minute how that is computed. And this is how these researchers define similarity index in different ways. I'm going to share just one of them with you. If you are interested, you can check the paper later. But what they did is the following. Okay, so you have two graphs, and you compute the Pareto eigenvalues of each of the graphs, okay? And then what they do is they measure how similar the graphs are by doing the following. The numerator here is how many Pareto eigenvalues the two graphs have. And then the denominator is computing the amount of Pareto eigenvalues between the two graphs, right? It's the intersection between the union, which is a number which is in between 0 and 1. Okay, what do you when is going to be this index equal to 1? Okay, so in this case, it's equal to 1 when the number of Pareto eigenvalues that they have in common is equal to the total amount of eigenvalues, right? So basically, that is true when the two graphs have the same Pareto spectra. Do you agree?
Are these sets multi-sets?
Actually, that's a very good question. And I don't think so. I mean, when I read the paper, I don't think that they mentioned, that's a very good question. They just listed, to be honest, I don't know. My guess is no, that they are not multi sets, but I cannot say for sure. Very good question, Kanan.
Seems like
Okay.
you probably don't want them to be multi-sets, or else the denominator will just be larger.
Mm-hmm. Yeah, that's why I said that. My guess is not, but I don't know for sure. It's the same thing as with the with the regular eigenvalues, right? Okay, so when is this index going to be 0?
Like G
When
and
they are
H don't,
destroyed.
yeah, when they're destroyed.
Well, exactly, when they don't have any Pareto's eigenvalues in common, right? Perfect. So, okay, let's just go back to our original example. These two, with respect to the best polynomial that they had in the literature, they had the same generalized permanental polynomial, right? However, with the Pareto eigenvalues now we can distinguish them. And we don't have 1, we have 0.74, okay? So, why did I think that this could provide more information? So the eigenvalues of the adjacency matrix, as we have shown, provide global information about the graph. But what the Pareto eigenvalues do is they look also at connected subgraphs, and they look at how they look at the similarity between subgraphs and how and the outward flow from those subgraphs, both. Okay, so that's why they expected this measure to be better than the ones they had before. Okay, so let's just go to the question. So what are the Pareto eigenvalues? And in order to define that, I have to talk about the eigenvalue complementarity problem. Okay, so let's see. I mean, this is this problem was introduced by Seeger in 1999, and this is the paper where they introduced this problem. And as you're going to see, it's a generalization of the classical eigenvalue problem that you learn in linear algebra. Okay, so let's just refresh our memory of what we know. So if we have a matrix, and we are going to be talking about the real classical eigenvalue problem. We are going to focus on the real eigenvalues, okay? When you have a real matrix, if you want to compute the real spectrum, what do? We compute lambda real and non-zero vector, real vector x that satisfies this condition, right? Okay, so notice that this implies that x transpose ax minus lambda x is 0. This observation is very silly because obviously if you multiply any vector by 0, you get 0, right? However, this is going to be very important in the generalization. Okay, notice that from this third condition, since x is non-zero, we can actually find an expression for the eigenvalue in terms of the matrix and the eigenvector. And actually, this has a lot of importance when you are applying certain algorithms like the power method, for example. This allows you to you compute an approximate eigenvector, and that allows you to get back an approximate eigenvalue. Okay, so so lambda is a real eigenvalue, x is a real eigenvector, and all those solutions is the real spectrum. Okay, so some key silly observations. The eigenvectors belong to Rn, right? As you know, Rn is a vector space over the real numbers. And it has this property as a particular property of our vector space. If you have any vectors in Rn and you multiply by a scalar that is non-negative, you will stay inside of Rn, right? Now, this particular, when we restrict alpha to be non-zero, is a property that defines subsets of Rn that are called cones. Okay, so a cone, so let's just, so any subset of Rn is a cone if it is closed under non-negative scalar multiplication. It doesn't have to be closed under negative scalar multiplication. Okay? Okay, can you give me an example of a cone in Rn that is not the whole space?
Vectors with only positive coordinates.
Exactly, that is the non-negative orthant, right?
Just like between any two lines.
Exactly, two lines. Perfect, two lines passing through 0, right? They form a cone. Perfect.
Wait, are those all the cones, right?
Say it again?
Like in R2, those are all the cones, right?
Oh yeah, but I mean in general, yeah.
Oh yeah.
I mean one line is also
true.
Right?
Yeah.
Okay. Okay, so this is another type of example in R3, right? Which is a cone, but is is closed under non-negative scalar multiplication. Okay, now we are going to consider an additional property. A cone is said to be convex if it is also closed under addition. Okay, so these two together doesn't make, if instead of having here non-negative scalar multiplication, we had a scalar multiplication, we would have a subspace, right? But here what we have is closed under addition and closed under non-negative scalar multiplication that makes a convex cone. Okay, can you give me an example of a convex cone and a cone that is not convex?
I mean, again, the non-negative orthant is a convex cone. A
Okay.
non-convex cone would be like, maybe you could take two lines that are very close to each other. I don't actually know.
I mean, if you have two lines, as you say, right, is it closed under addition? No. If you pick
Yeah.
a vector in this on this line and a vector on
Yeah.
this line, their sum is
Oh yeah,
outside
yeah,
the
that's right.
line, right?
Yeah.
So that is a very good example of a cone that is not convex. Perfect. Okay. And this example as well, the one that we just mentioned before, right? If we pick a vector up here and a vector down here, their sum is not in the cone. Okay, so, and this is an example of a convex cone, right? And actually this is going to have, this is actually very important. This is called the Lorentz cone in particular. Actually, convex cones are convex sets in the sense that if you have any 2 points, the segment containing them has to be completed included in the set. So that is a good trick to check if it's convex. Okay, and we are going to add another property, which is closed. So a cone is closed if every convergent sequence of points inside of the set, the limit is also in the set. Okay, I don't know if you have seen this before, but basically imagine that these blue points, right? These blue points are converging to this S point up here. So for the set to be closed, we need this point to be inside, right, of the set. So for example, you were talking about the non-negative orthant, so we want the whole boundary of the set to be included in the cone. And these properties are important because of the algorithms that are used later. Okay, so examples of closed convex cones are N for sure. Another example is any subspace in Rn. Polyhedral cones, which are the intersection of a finite number of half spaces, like this one. And in particular, the one that you guys mentioned, the non-negative orthant. And another one is the Lorentz cone, which is the one that I showed you earlier. So these are a few examples of closed convex cones. So, okay, another important idea in order to get to the definition of the eigenvalue complementarity problem is the concept of the dual cone of a cone. So if you have a cone, the dual cone is any vector in Rn such that x transpose y is larger than or equal to 0. What does that mean geometrically speaking? What is a geometric interpretation of x transpose times y larger than or equal to 0?
I guess the dot product.
Yeah?
The dot product, like considering the dot product.
Yeah, but geometrically, right? How do you know if two vectors have a dot product that is larger than or equal to 0 geometrically? What is the geometric interpretation of that product being non-negative?
I guess it's like one of the vectors is kind of tough to say actually. Yeah, like
I
one of the
guess
vectors is kind of pointing more towards the other vector.
The cosine of the angle between the vectors is, I think,
Aha!
The
The projection
projection of the vector
positive.
on the other.
yeah.
Okay, so what does it mean about the angle?
It's a cube.
Exactly. That's the idea. So what we are looking is for vectors that form an angle that is either acute, in which case is positive, or the vectors are orthogonal, right? So the worst possibility is that the vectors are orthogonal, right? That's the idea of dual cone. You have all the vectors that form an angle of at most 90 degrees with the ones that you have in the original cone. Okay, so something just for your is the dual cone is always a closed convex cone, and we're going to call self-dual cones that are equal to their own dual cone. Okay. Okay, let's just do an exercise. What is the dual cone of Rn?
Isn't it like all of Rn? Or
Okay, so notice that if a vector in Rn is in the dual cone, it must form an angle which is at most 90 degrees with all the others, right?
So just zero?
Exactly, Ryan. It's zero. So the dual cone of Rn is zero. Perfect. Okay, what is the dual cone of a subspace?
I feel like it would be like basically I don't know what the linear algebra term is for it, but like basically everything that's like independent of the subspace.
Independent?
Like if you have like look, for example R3 and like the subspace is R2, like basically like that other copy of R1 that like is
Okay,
not part of.
okay, so let me clarify something. Tanvi, your idea is good, but okay, so if you have R3, any subspace must consist of vectors in R3. So R2 is not a subspace. However, any plane going through zero, which is isomorphic to R2, is a subspace, right? So let's just think about your example again. You have a plane going through zero in R3. What would be the dual cone of that plane?
Like basically the line going through zero that's like perpendicular to the plane.
Exactly, exactly. And that has a name in linear algebra, which is called the orthogonal complement. Okay? Excellent. Okay, so if we for the polyhedral cone, right? For a polyhedral cone, the dual cone is also polyhedral. So this is an example. The blue lines form the cone K, and then the red ones form the dual cone. Why is the red one the dual cone of the blue one?
Like you're basically rotating each line 90 degrees
Oh,
above the origin.
Exactly, exactly. So notice that this red line forms 90 degree with this one, right? So it forms less than 90 degrees with any vectors inside of the blue cone. Exactly. And the same thing with this line, right? This line forms 90 degrees with this blue line. So perfect. So that's how the is cone. Okay. Can you give me an example of a cone that is dual to itself, self-dual? We have already mentioned that cone today.
Just zero?
Okay, what is a dual cone of zero?
Oh, I guess it'd be the whole space.
Uh-huh. Okay, so how about think about this idea. Imagine that the cone was formed is the non-negative orthant, right? If instead of being these blue lines, it
Wait,
was
so if the two lines are perpendicular?
exactly, exactly. That's what I'm saying. So if the cone, I mean, it's the two lines, right? Is these two black lines and everything in between, right? So as you said, if the two lines are perpendicular, then it is a self-cone. It's a self-dual, which is the non-negative orthant. Okay. So the example is that Lorentz cone is a self-dual and the non-negative orthant as well. Okay. So now we can define finally what is a Pareto eigenvalue. So if we go back to the eigenvalue problem, we have A is a matrix, a real matrix. We have a closed convex cone, which is Rn. And we are looking for a real number and a non-zero vector such that x is in Rn, ax minus lambda x is in the dual cone, right? Because 0 is in the dual cone of Rn. And we have this extra property, which in this case is redundant. Okay, so how about if we replace Rn by any closed convex cone? So now what we would have is that x must be in the cone, ax minus lambda x is in the dual cone, and this extra condition must happen. So this condition now is non-trivial anymore because now the dual cone doesn't have to be necessarily zero. And this condition is called the complementarity condition. And notice that what it's saying is that x and ax minus lambda x must be orthogonal, geometrically speaking. Okay? And actually, this condition allows us to recover the eigenvalue from X the same way we did in the regular eigenvalue problem. So the lambda in this case is called a k eigenvalue, and X is called a k eigenvector, and we also have a k spectrum. So everything we said for the regular eigenvalues, now you have in the general case. And these eigenvalues have applications in a lot of areas, in graphs, in physics, in economics, in mechanic systems. I mean, there's a lot of applications in many different areas. So what are the Pareto eigenvalues? So what we are going to consider is the non-negative orthant as the cone. And therefore, the problem now is finding an eigenvalue that satisfies this condition. X must be a non-negative vector. Ax minus lambda x must be a non-negative vector. And they have to be equal, they have to be orthogonal. So in R2, we would only have two options, right? That the eigenvalue is on one side and the Ax minus lambda x is on the other side of the quadrant, right? But in higher dimensions, you have many more options. So lambda satisfying this condition is what's called a Pareto eigenvalue. And this is the Pareto eigenvalue problem. Okay? Now, what happens with the Pareto spectrum? So there is, when you have a matrix of size n, the maximum number of real eigenvalues is n, the size of the matrix, right? For the Pareto spectrum, things work quite different. You may have no link between the order of the matrix and the number of Pareto eigenvalues. A large matrix may have one Pareto eigenvalue, and a small matrix may have a very large number of them. It is possible that there is no Pareto eigenvalue, which is a regular eigenvalue. And you always have a finite number of Pareto eigenvalues. And I mentioned that because with other cones, that is not necessarily true. So this is just a thing that is a curiosity. So the maximum number of Pareto eigenvalues of a matrix of order n is not n. For example, for matrices of size 2, the maximum is 3. For matrices of size 3, the maximum is 9. For matrices of size 4, the maximum is 26. Notice that it has been a long time to actually just say something about matrices of order 4. So this can tell you that finding the maximum number of Pareto eigenvalues is a difficult problem. It's not trivial whatsoever. The only thing that we can say, one of the things that you can say is that it's bounded by this number, but notice that this is quite large, right? It's an exponential number. So for matrices of moderate size, actually we can reduce, this is true for matrices of all size, but in terms of algorithms, we can reduce the problem to compute the standard eigenvalues of principal submatrices. So what do you think that in a graph a principal submatrix represents? Okay, a principal submatrix, let me explain, is that you pick, you have a matrix of size 3, okay? And you pick the first row, the third row, and the first column and the third column. So you pick a subset of the number of rows and columns, the same row indices for the rows and the columns, and that forms a principal submatrix, right? So what do you think that represents in the graph?
The subgraphs you get by taking out some vertices or some nodes.
Exactly, is the subgraph induced by those nodes. Exactly. So what we are going to be saying is that these Pareto eigenvalues actually give us information about the subgraphs of the graph, right? For example, imagine that you have a matrix A and you consider the first k indices. So Aj is the principal submatrix with the first k indices. So what you have to do in order to find the Pareto eigenvalues, for this particular submatrix is you find the eigenvalues of AJ that have a positive eigenvector, and then you check, this is a neighborhood property, that C, which is this submatrix down here, multiplied by phi of C is also non-negative. And then you repeat this for every principal submatrix. So this is the way that you would compute the Pareto eigenvalues. In practice, there are much better algorithms, but this gives us a sense of why this problem is connected to the graph problem that we talked about originally. Okay, so more formally, this is the idea, right? You pick any subset of the n nodes or n the first the 1 through n, and then you compute an eigenvector, an eigenvalue of this submatrix, and then you check the neighborhood property. And then what you do is those eigenvectors, in order to find a Pareto eigenvector, you just complete with 0 so that the vector has the right length. Okay? By the way, Simon, I still have a few more slides to go. I don't know, it's 10:30. I don't know if I should stop here or if you think I should move on. What do you think?
No, go ahead.
Okay, so this is a small example, right? For example, if we consider J equals 1, 8 is the submatrix, the principal submatrix, right? So in this case, what would be an eigenvector? 1, 8 times 1 equals 8 times 1, right? So an eigenvector would be 1, an eigenvalue would be 8, and that would satisfy the first condition. But now since 3 is positive, 3 times 1 is non-negative, so that is a Pareto eigenvalue. For j equal 2, however, 4 is not a Pareto eigenvalue because even though we have a positive eigenvector, 1, this is negative, so if you multiply, the neighborhood condition doesn't hold. And then if you consider the whole matrix, which is a principal submatrix, in this case, the standard eigenvalues are 5 and 7, and each of them have associated positive eigenvectors, so both of them in this particular case are also Pareto eigenvalues. So you have the 3 of them. So notice it's a 2 by 2 matrix, but we have three eigenvalues. Okay, so now we can go back to our original problem, right? So the standard eigenvalues, as we said, provide global information, and as we have seen, the Pareto eigenvalues give you information about deeper information. It gives you information about the subgraphs as well. And so actually, more formally, you can define the Pareto spectrum of a matrix as the largest, the largest eigenvalue. This is the spectral radius of each of the connected subgraphs. Okay. And so when G is a connected graph, the set of Pareto eigenvalues have more properties than when the matrix is a general one. The first one is that we always have eigenvalues. Okay, so if you have, in general, any matrix may have 0 real eigenvalues, right? In this case, the Pareto eigenvalues always exist, and they are finite, as we said. And in this case, we always have at least n, if n is the number of nodes, right? Which is the opposite of what happens with a matrix, with the regular eigenvalues. With regular eigenvalues, we have at most n. In this case, we have at least n. And the smallest number of eigenvalues are achieved by the simplest graphs, the path, the cycle, a star. And in this case, there is always one regular eigenvalue, which is Pareto, which is the spectral radius, which is the largest one, right? And the reason, but in general, the number of Pareto eigenvalues is much larger than the number of regular eigenvalues of the adjacency matrix, and that's why it provides much more information than the regular spectrum. Okay. So revisiting the example that we had before, how do we know if this index 0.74 is high or low? We haven't shown that with this index that we define, actually the index can reach 1, right? Okay, so what we can see here is that this is a table that gives you the mean and extreme values of the spectrum of the index that we have defined on pairs of connected graphs. So for example, for smaller graphs, right, you have that the average is 0.55 and the maximum is 0.8 and the minimum is 0.3. So this doesn't totally, but this index doesn't tell you exactly when they are isomorphic, basically. However, as the number of nodes increases, this minimum tends to 0, this maximum tends to 1, and the average value becomes smaller as well. Okay, so we are reaching the end of the talk. So what is the take-home message? So we have explored how traditional methods for comparing graphs can fall short. And this led to a fascinating new concept, the eigenvalue complementarity problem and the Pareto spectrum. And we have shown how these eigenvalues offer a powerful way of measuring graph similarity, and they provide deeper insights into complex networks. So if you want to learn more, I'm going to give you some possible ways of studying more about this if you like it. So there are other ways of measuring similarity between graphs using the Pareto. And this is one of the papers in which you can read other possible indices. And this is another paper that is even more recent from 2023. And another possible task for you to explore, we have seen the Pareto eigenvalues are linked to the cone non-negative orthant. But how about if we, instead of considering the non-negative orthant, we consider the Lorentz cone? Then we would have the Lorentz spectrum. Okay, what happens in that case? Surprise, surprise. Something that is very different with respect to all the other eigenvalues problems that we have discussed today. The Lorentz spectrum can be infinite, which makes it even more interesting. Okay. Okay, so thank you so much for being here today and your participation, and I'm going to stop here. If you have any questions that I can answer, I will be happy to do so.
What about like ways to like measure similarity between graphs that like don't use like spectrums? For example, like what if we do like a form like edit distance or something, where like you can like add or remove like a vertex or an edge or something like that?
Yeah,
That makes
actually,
sense.
yeah, you are right. You can measure, let me go back. In this paper here, in the one from 2021, they actually also define other ways of measuring similarity, looking at induced subgraphs.
Okay.
So you're right. These are not the only ways in which you can mean. But the funny thing is that as far as I know, so far it's still open question how to find an index that allows a mathematical fingerprint that allow you to determine easily when two graphs are isomorphic or not. So this is still open, right? So
Like,
yeah,
is there a way to compute
yeah.
the spectrum like efficiently that's not just like taking it's like faster than just taking the determinant? Like how do we
Okay,
like
so yeah, actually, this is the same. Computing eigenvalues is a very difficult task, right? Even for regular eigenvalues. And so what happens is that
like
the
like
same,
special eigenvalues, right?
sorry?
Like these eigenvalues have like a nice form. So is there a faster way we can compute them?
Yes, there are special eigenvalues to compute them. Now, what happens is that what they are researching now, and actually that is mentioned here, is that if sometimes instead of computing the whole Pareto spectrum or complementarity spectrum, what they do is they compute the largest ones. Apparently, the largest eigenvalues provide more information than the smaller ones.
That's interesting. Okay.
Okay, so if you can create a score that is based on ordering of the eigenvalues, and actually you know when you are computing eigenvalues in general, you have algorithms that target a particular subset of the eigenvalues. You don't need to compute them all, or you don't have to compute all necessarily, right? So you have algorithms like QR that give you all of them, but there are other algorithms like the power method that give you one, or there are other methods that give you a few. So there are many algorithms. I mean, I didn't have time for that, but if you're interested in algorithms, I can also send you some. And actually, here in this paper, they have a short paragraph saying that this idea of computing the largest eigenvalue of the principals of matrices is efficient only for moderate matrices for obvious reasons, right? Because the number of principals of matrices grow exponentially as the matrix grows. But they also mention some algorithms that are efficient for matrices larger matrices, right? So
That's
yeah.
cool. Great.
Okay, good question.
Are there any other questions? Well, if not, let's thank Maribel for a great talk, and then we'll move on to the next part of class.
Thank you, Simon. Thank you, guys. It was a pleasure.